Hello, everyone. Thanks for joining us today. Today, we're gonna host Miguel. Miguel is a lead research scientist at Hydra, where he focuses on modeling and optimizing industrial systems. Before joining Hydra, he completed his PhD in artificial intelligence at TU Delft, where he was advised by Franz Holyoak and Matthias Spahn. The floor is all yours, Miguel. You can get started.
Awesome. All right. Yeah. The stuff I'm going to talk about has little to do with what I do now, but some of the problems that I work on, are in a way like or also suffer from what I'm going to discuss. Okay. So the title of my talk is Policy Confounding: Causes, Consequences, and Corrections. So I'm just going to start with this sentence. This morning, I went to the kitchen for a coffee. When I arrived, I forgot why I was there, so I got myself a coffee. I'm sure you can relate to this type of behavior. This is something we often do. We do things not because we were meaning to do them, but simply because we're used to do them. So in this case, I got the coffee not because I wanted it, but simply because I was in the kitchen, and that's what I normally do when I'm in the kitchen. What I'm gonna argue in this talk is that RL agents also suffer or maybe benefit, depends on how you see it, from this same type of phenomenon. So I'm gonna start with an example that kind of illustrates this idea. This is a very popular POMDP environment, or a variant of a very popular POMDP environment, which is called the DMAze. And the task is relatively simple. The agent starts at the start location, and it receives a signal, either green or purple. And depending on the value of the signal, the agent either moves to the green goal if the signal is green, or it must move to the purple goal if the signal is purple. It's very important that the agent remembers the signal at every cell in the maze, such that it can tell where to go, right? Because the signal is only sent to the agent at the start location. So when the agent is just behaving random, then it needs to recall the signal that it received, such that it can tell where to go. Now, this is only true if the agent is, again, exploring the maze randomly, because if the agent finds the optimal policy or an optimal policy, like the one here, green arrow or green path for green signal, purple path for purple signal, then it turns out that the agent can ignore the key as long as it consistently follows these two paths. Because the reason is that the agent can infer the value or the color of the signal based on its own location. So the agent can the agent can say, well, if I'm in the green path, then I must have received the green signal, and if I'm in the purple path, then I must have received the purple signal. So this means that at any cell in this maze, the agent can just use its own location to determine where to go. By the way, if anything is not clear, please interrupt me and ask questions if you need it. Otherwise, I'll just continue. Any questions so far? Good. Oh, sorry. Maybe go back. Yeah. Cool. All right. So before I explain why this is happening, I'm gonna introduce some notation. Here we have F. F is just a set of state variables. So we represent the states using state variables or state factors, and these variables just define certain properties of the environment. So the state space is the Cartesian product of these state variables, and then what we call phi, it's a state representation. So it's basically a function that projects the original state space into a lower dimensional state space. So this is kind of like an state abstraction function. So all phi does is it selects a subset of the state variables, f bar, and then therefore by selecting some of them and ignoring the rest, it reduces the size of the state space. So S bar is the Cartesian product of the remaining state variables after applying the state representation. Any questions so far? Cool. All right. So let me explain why this is happening in the T-Maze environment. Why is it that we can actually ignore the signal after we find the optimal policy? Here is a dynamic Bayesian network that represents the dynamics of the environment. And in this particular environment, we have three variables: the goal, G, X, which is the signal. The signal takes the value of the goal at the start location, and then the location of the agent. The goal is hidden to the agent, so the goal is sampled at the start location, but it's hidden, and it's only the agent can only know about the goal through the signal, which the agent receives at the start location. And then we have the location, which is affected by the action, and the action here is shown as an exogenous variable. So the action could take any arbitrary value. Now, in principle, because this is a POM-DP, then you probably know that in general we need to condition on the entire state action history. So in this case, it will be the entire history of states, in this case X and L, and actions. So let's say that the task for now is just to simply try to predict the reward at time step 8. Now, in principle, if I want to do that, I need to know the location of the agent, because the agent could be at any of the cells in the maze. And I also need to know the signal, because if the agent is at any of the goal cells, then it can receive either a +1 reward or a -1 reward, depending on the value of the signal. The signal that defines the goal, or the goal defines the signal, but it's literally just the same thing. So in general, or in principle, in this particular environment, if I want to predict the reward at time step 8, then I need to condition on the location of the agent, and I also need to condition on the signal. Okay, so this is what we call like a Markov state representation, or in this case, this was the minimal Markov state representation. And this is just a definition. If you're familiar with the state abstraction literature, this is similar to MDP by simulation or model irrelevance state abstraction. And this is all this is saying is basically that you can use the reward. You can predict the reward or estimate the reward using this state representation, in this case, the signal and the location. And you can also estimate the transitions to the next abstract states. And all this means is essentially that you can solve the MDP by just simply conditioning on these two pieces of information. Any questions so far? Cool. Then we define the pi Markov state representation, and this is the same, but only when we follow a policy pi. So in this case, pi could be, the optimal policy that I had in one of the first slides. So green path for green signal, purple path for purple signal. So you just need to be able to predict the reward in the states that the policy is visiting, and the same with the transitions. Cool. Now, before I had that the actions were exogenous variables, but now I'm gonna condition the actions, or I'm gonna add the policy on top. So now the policy will affect the actions, which will also be affected by the state variables. In general, like if you follow an arbitrary policy, this is not really the case. The actions can be considered exogenous because nothing is really telling the agent what actions it should take. But if the agent finds a good policy, then it normally listens to the state variables. And in this case, because this is the optimal policy, it's at least initially listening to the location and the signal. Now, under this scenario, we already know that simply conditioning on the location is sufficient to be able to tell what the reward should be. Because being at location green goal implies having received the green signal. So I don't need to really keep track of any other information other than the location in order to be able to predict the reward. Any questions?
I have one. Why are we using state abstractions?
Yeah, we're not at the moment. I'm just trying to kind of set the stage, but we're not really using any state abstraction. I'm just arguing that depending on what policy you're following, you need to use less or fewer or more variables, right? So if you're just following an arbitrary policy, then in principle, in this environment, you need to condition on signal and location. If you're following the optimal policy, like the one depicted here, you just need to condition on the location. Does that make sense?
Isn't it sounds like a goal condition reinforcement line kind of policy?
No, it's just the task here is simply to predict the reward. So I'm just saying, okay, what do I need to predict the reward?
Predict the reward or accumulate the reward? I mean, accumulate the return.
Right?
Is it predicting the reward or accumulating the return? I mean, accumulating.
Yeah, well, in general, in RL, you need to predict the return or the value, and you also need to predict the transitions in principle.
You don't have to,
it turns
right?
out that
if it is model free, I don't have to predict the transition. I can do.
You don't necessarily need to predict the transitions, but you kind of implicitly do because if you're predicting the value, that means that you're not predicting the transitions, but you're storing enough information such that you can predict the next abstract state. Does that make sense?
Actually, TD learning inherently captures the dynamics. Like TD is sort of sample-based learning, Monte Carlo or TD, typical. Right. You don't have to literally learn if you're talking about model-free kind of setting.
Yeah. I'm talking about model-free. So, but what I'm arguing is that if you want to predict the value at any state, you do need all the information that is important to predict
enough samples.
Enough,
sort of estimated better.
Enough variables in this case. I'm talking about variables. So you need to keep track of, in principle, for any policy, you need to keep track of at least the location and the signal.
Right.
To predict the value. Otherwise, there's no way you can predict the value without these two pieces of information.
Right.
Yeah. And this is kind of like what the whole state abstraction literature talks about, right? It's not sufficient just to predict the reward at the current time step. You also need to be able to predict what they call the next abstract state, and the next abstract state is defined as is defined by the state representation itself. I think you're right. In essence, you only need to be able to predict the value. So you need to keep track of all the information that you need in order to predict the value.
Mm-hmm. Also, I feel like, I mean, I may be wrong, please correct me. I think state abstractions or state action abstractions are generally used to minimize your, sort of reduce your state space or action space dimension.
Yeah.
To learn policy, to converge to an optimal policy quicker.
That's right. Yeah.
Right. Okay.
That's correct. Yeah. In this case, the way in which you reduce the state space is by ignoring some of the features, because ignoring some of the features implies that you have a smaller state space. Right. So now, your state space initially is just the entire history of states and actions. If you then just focus on the location and the signal, then your state space is much smaller. If you now only focus on the location, your state space is even smaller.
Right.
Yeah.
And then how you were talking about POMDB kind of setting, right?
Yeah, in the POMDB setting, you can think of the states as the histories.
Yes. So you're assuming that it is a POMDB setting. Is that
Not
observation?
necessarily. This also happens in MDPs, as I will show you later
Right.
in another
Okay.
example. But yeah,
Okay.
like this
Okay.
is broader than MDPs or POMDPs. This is just, in this particular case, it happens to be a POMDP, but like you can think of a POMDP as an MDP where the states are the histories.
Right. Makes sense.
Cool. Thanks for the question. All right, so where were we? Okay. So under the optimal policy, because the agent is only following these two paths, then it's sufficient to condition on the location in order to predict the signal. Sorry, in order to predict the reward at time type 8, and in fact, in order to predict values or to predict transitions, location is sufficient as long as you follow the optimal policy. Cool. But now the picture is like a bit too complicated to understand why this is happening. So let me simplify it a little bit. Here I've grouped together all the states and actions in the history up to time t. And I'm using FT to denote those. So FT is the state action history up to time t. And then I have FT plus 1, which is the state action history up to time t plus 1. And as you can see here, the policy is affecting both FT and FT plus 1. And I'm not sure if people are familiar with causal inference, but for those of you who are, you may recognize this picture. This is a clear example of confounding, where you have a variable that is affecting two variables at the same time, and this variable may or may not introduce spurious correlations between these two variables. So in this case, the spurious correlation is the correlation between the green goal, or the location being the green goal, and having received the green signal. There's nothing in the environment that forces the agent to having received the green signal when being at the green goal. This is just something that the policy is introducing. Like it's a correlation that the policy itself it's creating. But this correlation implies that if I'm at location green goal and I'm following the optimal policy, then I must have received the green signal. And this is why you can ignore the signal, because the policy has introduced this correlation. However, if we now intervene in the environment, and this is what this do operator does, if we now set the value of green goal, of the location to green goal, and we ignore the policy completely, we just take the environment and we just put the agent at the green goal, regardless of what policy the agent is following, then the reward could be either +1 or -1. Before, if we just sample from the optimal policy, there's just one option. When you're at the green goal, then the reward must be +1. If we intervene in the environment and we set the value of the green of the location 8 to green goal, then we have these two options: +1 or -1. Is this clear? This is the do notation in causal inference. It basically just means intervening in the system, in the environment in our case, and setting some of the values of certain variables to a particular value. Cool. And using also this notation, this is how we define policy confounding. So we say that a policy is confounded if the reward under a particular state representation is not the same. We say that a state representation is confounded if the reward under that given state representation is not the same when we intervene in the environment than when we just sample from the policy. And the same goes for the transitions. Cool. Yeah, this is just some math, but essentially all this means is if I can predict the reward using the current policy, following the current policy, and that doesn't match the reward when I set the values of the variables to a given value, ignoring the policy completely, then we say that the representation is confounded. Cool. All right. So now a bit like I'm just gonna discuss more practically what this means, right, and why this is important. In principle, if you're following, if nothing changes in the environment, if you just follow the optimal policy, then this is no problem, right? Like you can continue sampling from the environment, you can continue following these optimal trajectories, and you should be able to solve the task. However, if we now force the agent to deviate from these trajectories, and we do this in this environment by introducing some ice in the middle of the environment, the ice is basically pushing the agent away from these two paths. So it forces the agent to move down when at the top cell and up when at the bottom cell. But then the ice is kind of confusing the agent because the agent is relying on its location. But then the agent does no longer know how to act because now location does not match signal. So the reason I call this out of trajectory generalization is to make the distinction with out of distribution generalization, which is a much broader problem. Out of trajectory generalization just means generalizing to other trajectories within the same environment, not necessarily generalizing to other environments or generalizing to other words, simply different trajectories. And I feel like that's something that all agents should be able to do, right? Like the agents should be able to work regardless of what trajectories they're following. Cool. Any questions so far? And I haven't talked about how these state representations are formed, but I'll do that in a second. Cool. All right. So when should we worry about this? Well, we should worry when we use function approximators. In principle, if we use tabular methods like tabular Q-learning or something like that, then we don't need to worry because we are storing all the information for the information for every state in a particular cell. So there's no state abstraction going on or anything. However, if we use function approximators like neural networks, then the function approximators will learn to ignore certain variables when they're irrelevant for the task. So in this example of the T-maze, the function approximator, the neural network, may learn to ignore the signal if the signal becomes irrelevant, as it happens when we follow the optimal policy. So this is a problem when we use function approximators, and this is also a problem when we train on narrow trajectory distributions. What I mean by narrow trajectory distributions is these trajectories that are very similar, and they're normally generated by very similar policies. If you train on like a very diverse set of trajectories, then the spurious correlations will probably not be present in all trajectories. So therefore, there is no risk of policy confounding. And this is kind of like leads to some kind of like ways of mitigating this problem. One is just use off-policy methods, because off-policy methods with off-policy methods you are not restricted to train on the same trajectories. You can train on any trajectories generated by any policy. Whereas with on-policy methods, you would need to train on trajectories that are generated by the current policy. Or you could also use exploration, like you could increase the exploration, or you could do domain randomization, such that you add more variety to your trajectory distribution. And both of these methods or both of these techniques have the same goal, the same underlying goal, which is to dilute the spurious correlations that some of the policies are introducing. Any questions so far? Okay. Here's another example. In this case, this is the key-to-door environment. So in this task, the agent starts at the start location here, and then it needs to collect the key and then move to the door. Initially, when the agent is just behaving at random, then the agent can ignore the key. Sorry, the agent needs to remember the key, because otherwise it doesn't know whether it needs to go collect the key or whether it can already move towards the door. However, once the agent has found the optimal policy, which is depicted by the purple arrow, then it can ignore the key after it's at any of the cells to the right of the start location. And the reason for this is that being at any of these cells implies having the key under the optimal policy. So by the time the agent is at the third cell, the agent can tell, well, I already have the key, so I don't really need to go back. And it can infer that based on the location. Any questions about this environment? Sorry?
But then at cell 3, let's just say that I didn't took the key, I forgot. Should I go back and pick it up? I don't know that. I'm assuming that I already have the key.
Right. Under the optimal policy, that cannot happen, right? Like by the time you're at cell 3, you have the key, because like the optimal policy is like move left and then right. So then by the time the agent is at cell 3, it has the key. That's the only option.
Right.
Cool. And this is like, like two kind of like two binary cases, either random or, optimal policy. But I'll show later some numbers that make this a bit more intuitive. Like what happens if like the agent has the key 99% of the times versus like, this 1% of the time not has the key. Cool. Here's another environment. The two previous environments were POM-DPs, but this is an MDP. In this task, in this environment, the task is really simple. Oh, by the way, in this environment, we train the agent starting from the start location, the start train, but then we evaluate the environment starting from another location, from start eval. And when we evaluate the agent, when we force the agent to start at a different location, the agent does no longer work, because it thinks that it has already got the key, because it's at the cell that is next to the door. So under the optimal policy, that being at that cell implies having the key. Okay, in this environment, the agent just needs to move from the start location to the goal. And ignore the yellow square for now, but the task is just that, like the agent moves from the start location to the goal, and the states are represented by two variables. One is the columns, and the other one is the rows. So the row is just a binary variable for bottom row or top row. And then essentially what happens is, in this environment, the agent initially, needs to pay attention to the row variable, but eventually once the agent finds the optimal policy and it follows it consistently, then it can ignore the row, because it's always at the top row. So why should it pay attention to the bottom row? In the evaluation environment, we force the agent to move down, and then the agent does no longer work anymore. This is surprising because during training the agent can actually move to the bottom row. It's just that at some point it just starts following the optimal policy. It never visits the bottom row, and it learns to ignore the bottom row. Here are some results showing precisely this. So the first one is the teammates environment. Then we have the key to door, and then the diversion environment. This is just this last environment I just explained. And here you have like blue is DQN, and red is PPO, and then you have the dashed arrows. Those are that's the performance of the agent on the training environment, whereas the bold dash curves and the bold curves are the performance of the agent on the evaluation environment. So this is the environment where we kind of like change slightly the dynamics. We force the agent to move away from its preferred trajectories, such that we can evaluate how well it does out of trajectory. So as you can see, PPO struggles in the evaluation environment. So initially, the pattern is very similar in all three cases. Initially, it does well, also in the evaluation environment, but then the performance drops. And this occurs when the agent starts to follow or like sample the same trajectories and again and again. This is when the spurious correlations start to be more and more present. Whereas DQN, because you can train DQN is of policies, you can train on all trajectories, then DQN is much more robust to this issue. So DQN has a very large replay buffer, so you have samples where the spurious correlations are not present. Any question about this?
So off policy does better job in this context to solve the
Yeah.
policy confounding.
Right. And again, because with off policy, you can train on like many different trajectories, many different samples that come from different policies, and some of the policies do not, the correlations that we have, like between the key and the location, or between the signal and the goal, they're no longer present in those in all those samples. So the agent cannot rely on those to solve the task.
Makes sense.
Does that make sense?
Yeah. Thanks.
Okay. I'm not sure if there's anything else I want to say about this. Okay. If we now reduce the buffer size of the DQN method, then we see that DQN also suffers from this same issue. And the reason is the same, right? Like normally in DQN, you remove the old experiences. So if you remove too many of them, if you just leave the last 20K, then, the last 200, then the agent is basically training on the same trajectories, the trajectories that contain the spurious correlations, and it cannot perform well on the evaluation environment. In both cases, this is evaluation environment. And then I mentioned before that you could make things better by adding some exploration or domain randomization, and this is precisely what I'm showing here. If you add more exploration, if you force the agent to move away from these trajectories where the spurious correlations are present, then none of these two methods suffer from policy confounding. Okay. How am I doing with time? This is like half of my presentation. Okay. I think I'm on track. Okay. All right. So everything I talked about up to now is based on a paper we wrote last year that we published at RLC, and this is the new stuff from this year. This is a paper I wrote just a few months ago, and basically in this paper, I'm kind of like trying to solve this issue of policy confounding, and that's why I decided to title the paper "Breaking Habits." There were I proposed already two strategies to do this. One was like to add more exploration or domain randomization, and the other was just to use off-policy methods. But of course, none of these strategies are good strategies in my opinion. You still want to use on-policy methods because they might be, in some cases, they might be more efficient. And of course, you don't want to add a lot of noise to your environment or to your policy. So in this paper, I'm basically showing that if you use the advantage function, just the same advantage function that we all know about, then you can already mitigate this issue. And the advantage function normally, is normally used to reduce the variance of the gradient updates by subtracting the baselines. In this case, the baseline is the value function. But it turns out that it can also help mitigate policy confounding. And I'll explain why that is now. So here's how we define the advantage function with or under a particular state representation, phi of st. So just to clarify, phi of st is just like, you can think of it as like maybe the first layers of the neural network, which are the ones that decide whether a particular variable should be ignored or not. This is just a mathematical way of like expressing, that function approximators tend to ignore certain variables. And the reason why Q in this case is not affected by phi, the state representation, is because normally Q is estimated from samples, right? So we normally roll out the policy and then we get a reward, and that's what we use as the Q function or the Q value, the estimate of the Q value. Whereas for V is normally in most RL algorithms, in most on-policy algorithms, V is it's a network, it's a value function. So you kind of like you're modeling it with a function approximator with say a neural network, and therefore you know there's this risk of like the neural network ignoring some of the information if it's actually irrelevant. So that's why we have this asymmetry here between Q and V. You can question this assumption, but in many cases, in many algorithms, it holds. Okay, so under this definition, sorry, was there a question? Okay.
Are we doing in the context of online on policy?
This is on policy, yeah. There's no
right.
RL. This is just like interacting with environment. Sorry, when you say online on policy, you mean just a standard RL. Oh, yeah. I'm not sure you would use advantage functions with off policy. Maybe you do. But more normally the advantage function is used with the policy gradients. So yeah, this is policy gradient methods, actor critic, PPO, all these methods.
Right. Okay. Thanks.
Yeah. Cool. Okay, so it turns out that you can write this expression here, this advantage function in this form, and I'm not going to go through the math. It's in the paper. It's really simple. It's like if you look at it, it's just a few lines. But the important bit is this term here. So basically, this whole expression is saying, okay, the advantage function is proportional to the probability, or rather to the complement of the probability of a given state action pair, given that particular state representation, given the state representation that the agent has formed. And then we have this second term, which is like just the Q value minus some baseline, which is the average Q value of all possible state action pairs, and they are weighted by their likelihood under the state and the state representation. But again, the important bit is the term in the front, and this is important because this is showing that the advantage function upweights samples if they are less likely under the current policy and the current state representation, and downweights samples when they're more likely. And by samples, I mean state action pairs. And if it's not clear already why this is why this is important, and it makes sense that it's not clear because it's hard to understand what's going on here. I'm going to explain this with the same key-to-door environment that I already introduced. So we're going to focus on location 6 for now. When the agent is at location 6, there are two options really, right? Either it has the key or it doesn't have the key. So we're going to investigate, the different values of the advantage function and the Q value in those two possible cases. And we're going to do so also under different policies. So like the first row is just a random policy. There are two actions in this environment. So in this case, the probability of either of the two actions is 0.5. So just a completely random policy. And then as we move down the rows, the probability of selecting the optimal action increases. So we go from 0.5 to 0.9. And here on the right, we see the likelihood of being at location 6 and having the key. As you can already see here, when the agent is just behaving at random, the likelihood of having the key at location 6, it's already 0.83. This means that 83% of the times when the agent is at location 6, even when it's behaving randomly, it will have the key. So a very naive agent can just simply move to the right when at location 6, and it will get a reward of +1 83% of the time. So, the agent is kind of like very much incentivized to ignore the key, because, if 83% of the times I'm going to get the reward of +1, then, that seems like a pretty good strategy. And as the policy improves, the probability of having the key at location 6 also increases. So we go from 0.8 to 0.9999. And the important thing here is that the Q value doesn't change. The Q value is the same regardless of the probability of having the key. So this means that the agent is not more or less incentivized to ignore the key. It's just like same always. Whereas the advantage function, the value or the magnitude of the advantage function decreases as the likelihood of having the key increases. And this is important because the more samples that we have where the agent has the key, the less we want to reward, or the less we want to weight those samples. In the opposite case, when the agent does not have the key at location 6, and that's already very unlikely under the random policy, the reward is the agent is very heavily penalized for when moving right when not having the key. Whereas if we use the Q value, the agent always receives a reward of 0, or always perceives a value of 0. Whereas with the advantage function, can you actually see my cursor? Not sure if you can see. Oh, you can. Okay, that's good. So as you can see, like already when the probability is 0.5, the advantage function is penalizing the agent for taking the action move right when not having the key. And this is in contrast with moving right when having the key. And again, this is very important because this counterbalances this effect of the policy, whereby some state action pairs have more importance on the data set. You have like many more state action pairs where the agent has the key and moves right than pairs where the agent doesn't have the key and moves right. So you kind of need to counterbalance this effect, and this is precisely what the advantage function is doing. When the probability of selecting the optimal action is 0.9, the agent is very heavily penalized for taking the action right when not having the key, whereas it receives a very, very small reward when having the key. So I hope it's clear, the role of the advantage. For those of you who are familiar with causal inference, you can think of the advantage as like doing some sort of like inverse probability weighting, whereby the samples that are more common receive a lower weight, whereas samples that are less common receive a higher weight. And this is kind of like counterbalancing the effect of the policy. Cool. These are just some results showing that PPO with the advantage function is much more robust to out of trajectory generalization. So this is on the evaluation environment, whereas the PPO trained on the absolute Q value suffers from out of trajectory generalization or from policy confounding. And this is again the same three environments that I already introduced. Not sure if there are any questions about this. Cool. The results I showed before were also with PPO, and normally in most implementations of PPO, you use the advantage functions. The advantage function is the default way of like training agents with PPO. However, what happens is that in most implementations, you normalize the batches before taking a gradient step. And what it does, what the normalization does, is it removes this property of like scaling down or up the gradients based on the probability of those samples. So this first plot is showing that PPO with normalization it suffers. So this is the red one. whereas PPO without normalization, so if we just remove that normalization, is not affected, or is much more robust to policy confounding. And this is also if you increase the batch size, well, it turns out that you can also mitigate the issue of policy confounding. This is kind of similar to what I was discussing about using the off policy methods before. All right. Here's just some visualizations showing that on the left you have the Q value or agent strength using the Q value, and on the right you have the advantage function. And then these heat maps show how much attention the agent is paying to the key at any of the cells within the T-maze environment. Sorry, not within the T-maze environment, within the key two-door environment. And this is after 10K time steps. So the first one is 10K, then 50K, and then 100K. And you can see like the more yellow it is, the more attention the agent pays to the key, and the more purple, the less attention. So it's interesting that the agent that is trained on the with the absolute Q value pays literally no attention to the key at location 6, whereas the agent that is trained with the advantage function, it's very much aware of the key. It's selecting its actions based on the key. And similar heat maps for the T-maze environment. The agent that is trained with the Q value only pays attention to the signal at the start location, but then it doesn't really care about the signal anymore. So the more yellow the cell is, the more the agent considers the signal when selecting actions, and the more purple it is, the less the agent cares about the signal. So it's interesting as well that the agent with the advantage is paying attention to the signal at many of the cells. In some of the cells, the agent does not pay attention to the signal because it's actually quite irrelevant. So if you're at any of the cells on the top, regardless of whether the agent has received the purple or the green signal, the agent needs to move right? So or down, right? Like knowing the value of the signal doesn't really change the policy, and that's probably why the value of the signal or the attention that the agent pays to the signal is not as high. Cool. Like I said, this talk was based on 2 papers. The first one that we published at RLC last year, and this one I presented it at RLDM this year. Sorry, the first one I published at RLC last year, not this year. Cool. All right. Thank you very much, and I'm happy to take some questions.
Yeah. Thank you for a very insightful talk. I'd like to ask a few questions. I mean, I think most of these settings are discrete state action spaces, right?
That's correct. Yeah.
Did you test it on any continuous or large state action spaces or continuous state action space?
No, I didn't. The results, the theoretical insights apply to either discrete or
Yes.
continuous. But I haven't tested on continuous or more complex environments. The purpose of the experiments was simply to show the ideas behind
Yes.
the method, or not the method, but the ideas behind the advantage function and how it works. It was more it was more meant as like a conceptual way of explaining the intuitions rather than
yes.
Yeah.
Yes, makes sense. Yeah, really appreciate it. Thanks for giving a talk at of your. It was great. It was great to host you. Are there any other questions? Yeah, Prasanna. Yeah, go for it.
Hi, Miguel. Yeah, thanks for the talk. I'm just trying to understand the OOT, the out of trajectory generalization, and trying to understand if like is it an exploration issue? Like if we are not exploring enough. So like for example, if we use SAC or increase like the temperature parameter for exploration there, or in PPO, make it more explorative, would the agent trained on that hyperparameters, would it like figure out this like con- confounding?
Yeah, I think if you increase, in fact, there was like a graph showing that if you increase exploration, you could mitigate this issue a bit more. Let me try to find it. Here, this one here. I think, like you're right. Like if you increase exploration, then, the agent is behaving more randomly. So then, it's not as, the issue of policy confounding is not as severe, I think. However, at some point, like you really want to commit to particular policy, right? And I feel like, it's a way to kind of mitigate the issue, but it doesn't solve the issue entirely, right? Also, you could argue that, like in the teammates environment, if the say the corridor was larger, was wider, then being at any of the cells on the top will imply having received the green call. And if you added some exploration, you probably wouldn't leave the cells on the top. So like in some cases, you may not even solve the problem, or even in the key to door environment, even if you add enough exploration, you may not really reach the key when you are at any of the cells in the middle of the maze. So whether exploration works or it doesn't, it's not. I guess it's not a question. I think in most cases will mitigate the issue. I guess the question is how effective that is, and how targeted that method is. Sure, if that answers your question.
Yeah, I think that makes like sense.
Yeah, I feel like the advantage function is a much more elegant way of like of solving the issue, because it does the same in a way as exploration, because it kind of like compensates, kind of like upweights some of the samples more than others, whereas exploration is trying to like make the trajectories or everything more uniform. The like the advantage function is kind of doing the same, but implicitly, if that makes sense.
Okay. Yeah. Thank you so much for that answer.
Yeah, no problem. Thanks for the question.
No, if you guys don't have any questions, we can wrap up the session. Thank our speaker.
Cool. Yeah. Thank you so much for inviting me.
Yeah.
Yeah.
Thank you, Miguel. It was fun.